Okay, so yesterday I ended with a practice problem as I was introducing the idea of problem solving in uniform circular motion with a car driving around a 40 radius curve at 36 meters per second. And we were going to assess the coefficient of friction necessary to keep that car on the road. And as I was going through the problem, we were doing everything perfectly, but I got to the end and calculated it, and the answer I was getting was above 1. And I told you that we were only going to deal with materials where the coefficient of friction was below 1. Well, it turns out I just wrote a really bad problem. So 36 meters per second is about 80 miles per hour. And if you go around a 40-meter curve at 80 miles per hour, unless you're driving through tar, you are not going to stay in that circle. So let this be a public service announcement to always slow down. We would have needed a coefficient of friction of 3 point something, which, if you all of a sudden drove into tar and really had to trudge through it, we might be okay. But sure enough, not a very good example. Note to self, when you're physicsing bad, do not just make up a problem on the fly. So I'm going to revisit that problem with a more reasonable speed, one you should be doing when taking a curve of about 40 miles per hour. And then I will do another little video with another practice problem just to solidify the idea from yesterday. All right, so I'm going to share my screen with you and use a document camera to walk through the problem of yesterday with a much more reasonable speed. So give me 1 second to share the camera. All right, so we said that a car, this was going to be going a speed, and we're going to use 15 meters per second, which is closer to about 30 miles per hour. We're going to use a speed of 15. Well, I guess that's not right either, but anyway, it's more reasonable. 15 meters per second. And the radius of the curve is 40 meters. So again, why is this uniform circular motion? Well, if we look at this curve from kind of the top down view, we see that the car enters into the curve, and the curve can be modeled as a portion of a circle with radius 40 meters. And so during the curving part of the drive, if the car is going at a constant velocity, it will indeed be in uniform circular motion during that piece of the curve. All right, so we're going to then take that curve and we're going to flip it. So we're looking at a head-on view of the car. So here's the tail of the car, kind of going into the page and then turning to the right. All right, so what are the interactions on that car? So we said that there was the force of gravity between the car and the earth. We said that the car was resting on the surface of the road, so we have the car and the road, and that's that normal force. It's the force by the road. And then we said that if the car was going to slide off the road because it's going too fast, something's got to prevent it from sliding. And we know that things that are prevented from sliding are due to a static friction force. So that's between the car and the road as well. So if we draw a free body diagram of our car, we have the force of gravity, which we know is mass times gravity. We have the normal force, and then we have that frictional force, and it points in. The car wants to slide straight off the road, so the frictional force is in the direction towards the center. Now, as this car is turning, we know that the acceleration is towards the center. Remember, in uniform circular motion, the acceleration is towards the center. And so we will separate our forces into horizontal and vertical components. The horizontal, we'll number them, 1, 2, and 3. For the force of gravity, we don't have anything horizontal. Its magnitude is mg, and it's pointing down, so we put that negative in. For force number 2, we know that the frictional force is mu times n. It is pointing to the right, so it's positive, and our vertical position is 0. Our vertical component is 0. And then force number 3 is our normal force, and that is only acting vertically. All right, so our sum of our forces in the horizontal direction is the mass times the horizontal acceleration, and the sum of the forces in our vertical direction is mass times the vertical acceleration. The object isn't changing its motion up or down, so we know the sum of the forces vertically must be 0. And this is where we add that question to our process. What is the acceleration horizontally? Is it linear or is it rotational? And so that's that new question. It is rotational in circular motion. And so this is the mass times that centripetal acceleration, right? We add these together. We have n minus mg equals 0. And we have mu sub n equals mass times our centripetal acceleration. Okay, so we know that our centripetal acceleration is equal to the speed squared over the radius. Now we don't know n, but we do know from our vertical assessment that the normal force is equal to mg. So if I plug that in, I have mu times mg is equal to mv squared over r. And again, I'm trying to solve for that coefficient. So I'm going to divide both sides by mg, and I get mv squared over mg r. My m's will cancel each other out, so it does not matter what the mass of the car is. And we see that it's v squared over g times r. And so when I plug in my values for that, so 15 squared divided by 9.8 times 40, I find a coefficient of friction of 15 squared divided by 9.8 divided by 40, 0.57. All right, which is more related to a material that we said we would be dealing with in our class. Okay, so again, recognizing the interactions, drawing appropriate free body diagram, recognizing that our forces are acting in the horizontal direction and 0 in the vertical direction, that they are in circular motion horizontally, and then following our process to solve for the variable of interest. Right, so that takes care of the problem yesterday and reminds you to drive at more appropriate speeds when going around corners of 40 meters. All right, we will look at some more of these practice problems, but good job on this one.